Hello and welcome everyone. I am Ishanya Agrawal, one of the TA for Introduction to Deep Learning course. Today I'll be going through the recitation of datasets and data loaders. Our goal in this recitation is to get comfortable using the dataset and data loader objects. This is an important recitation as it sets the first stage of a data science project, which is preparation of data. Today, we will be covering data reading and saving in NumPy and Pandas, and we will introduce PyTorch datasets and data loaders, and we'll go through an example to create our own custom dataset. Also, we will look into data transforms and collate functions, which will come handy in homeworks part 2s. First, let's look at reading and saving in NumPy. As we know, NumPy is a powerful Python library which can store multi-dimensional array and matrix data structures using lesser memory and providing better computational efficiency. Hence, we will be extensively using it to store and load our data in future homeworks. .npy format is a standard binary file format in NumPy which is used to persist a single NumPy array on the disk. It stores the shape and the dtype information. I would recommend going to the documentation and read more about it. Here, let's see an example. So first, we create a temporary array of shape 3, 3, which is filled with ones. You can use np.save to save the array in the .npy format, and similarly use np.load to load that same .npy file. Now here we have a list of lists of different sizes which is converted to NumPy array. When dealing with NumPy array of varying row sizes or a list of objects or an array of arbitrary objects, we set allow pickle equals to true to save the object array. This helps in serialization, and similarly during loading we define the same argument allow pickle equals to true to load the file since one of a file is pickled. When you run these files, it gets saved, and here we can see the output of the loaded files. .npz format. So .npz format is a zipped archive of files named after the variables they contain. So in this case, we have a temporary array and a temporary array pickle which we defined above. And so these temporary arrays will be saved to temporary.npz, but we will be giving them two keywords because that's how we will be accessing it later. Here also we can save and load the file, and we set allow pickle equals to true because one of the arrays here we are storing is a pickled file. Please note that for saving the .npz files we use np.savez function. Now let's run it, and we can access it, and we can see that we can access these arrays using their names, using the variables we defined before. Moving on, let's look at these reading and saving in Pandas. For homework part 2s, we will be using Pandas data frame to store and create the Kaggle summation files. So here we first create an empty data frame using pandas.dataframe function, and we typically have a column of indexes and a column of labels. So we create a temporary data, and this is how the data looks. Now we can use output.to_csv function to save it as .csv file. We set index equals to false. If set to true, it will have another column which has indices in it. We will be using .read_csv method to read the CSV file as the pandas data frame object. Again, let's see the output. .head function in pandas basically returns the top 5 rows, so we can see 0 to 4 and their corresponding label 10, 11, 12 as mentioned here. Now let's move to PyTorch datasets and data loaders. Before moving forward, let's see how to manually load the data without using the PyTorch datasets. Suppose we have a sample data stored in a .npy file. First, we read all the data, we load the data and we read all the data and create our features and why. After that, we in our training loop, we can directly pass the entire data into a model and do the training. Feeding all the data manually is not a big deal when the data set is small, but as we know that deep learning model requires large amounts of data in order to reach superhuman performance. Computing gradients for all the data points is not efficient and hence we use batches. Divide the whole data into batch size and go through each batch at once and then recompute the gradient and update the weights. So here we are creating those batches manually and running our loop on the number of batches as well. While we can manually create the batches, but it would require a lot of effort to make the entire process efficient and optimized. Loading and pre-processing these large amounts of data requires specialized algorithms to do so in a computationally efficient manner. Let's look at some terminology first. So, one epoch is defined as one forward and one backward pass of all the training examples. Batch size is the number of training examples in one forward and backward pass, and number of iterations represents the number of batches. So, for example, with 100 training examples and given a batch size of 20, then it will take 5 iterations to complete one epoch. Dataset and DataLoader classes, which automates the above process using easy to use interface. Please refer to the official documentation to read more about it and see all the different functionalities it provides. So the way it works at a high level is that we have our dataset. The dataset class is the one that has access to our data, and the data loader class is the one that loads the data with the help of the dataset class. The training data you have is basically passed through the dataset class, and that dataset class creates a training data object, and that object is passed to the data loader. We will look in detail below the three functions which are required to be defined in the dataset, which are init, len, and get item, using which the data loader also loads and accesses the particular data it wants to. The data we can be indexed, and it can be images, audio, and their corresponding labels, or it can be just features as used in unsupervised learning. When this data is accessed by the dataset class, it can either be the attribute of the dataset class, or it can be via methods that retrieve the data from specific directories for long-term storage and load the data on the fly. Data loader is the one that actually loads the data and retrieves it. Data loader helps make batches, shuffles the data, and does parallel processing to make the entire process efficient, and then finally load it into the model. PyTorch gives a good range of preloaded datasets, few of which are mentioned below. It supports image and like MNIST, Cocoa, all these are image datasets. Then we have something in text dataset as well, like Amazon Review for your MNLI, and also there are datasets in audio. We feel free to explore more of it in the documentation. So let's work with one of the PyTorch provided dataset specifically provided by Torch Vision called Fashion Amnist. It is a sequence of images which contain some clothes, and image size is of 28 cross 28. The Torch Vision provides a dataset, and let's see that here we are creating our training data object and test data object by calling this torchvision.dataset class. Let's visualize. Let's first load it, and let's visualize. So as you can see, the labels, and here are the clothing items for those particular labels. So this is how our data set is. Now we got the dataset objects using the PyTorch dataset class for MNIST data. Now we pass that object to our data loader provided by torch.utils.data. we create two separate data loaders, one for training and one for testing. For training, we have shuffle equals to true, and for testing, it's false. Realize it, the data loader object can be accessed using the Python iter function, which basically returns the iterable. And the way you iterate over it is using the next function. This gives us one batch of training data. So let's run and see it. So here you get a batch size of 64. 1 represents the number of channels and 28 cross 28 is the size of the image. Labels are of size 64 since we have 64 images in the batch. Remember, we defined the 64 in our above data loader class. Moving on, let's look at our custom dataset. So since in previous we have worked with the dataset class which PyTorch provided on its own, let's now see how to create our own custom dataset. Torch.utils.data provides a dataset which is an abstract class representing a particular data. Your custom dataset should inherit a dataset and override the following main two functions, which are len and the get item. We can do some bit of pre-processing in the init function, which is a constructor, and this is typically where we have access to our data. We'll be using len function to get the length of the total data. It basically tells the data loader how many samples are contained in the dataset. This is used to know how many samples are in an epoch and how the data loader structures its batching mechanism. Get item, it takes an input, the index value of the dataset we want to access, and returns the data sample itself at that index in an order chosen by you. You can use get item to do some final processing on the data before it sends out. There is a caveat though, that get item will the amount of process you do in the get item should be as less as possible because it's called multiple number of times, which could be as high as millions depending on the sample of data. Hence, most of the preprocessing is done in init function. In future homeworks, you will find some of the cases where processing has been done in the get item as well. For the custom dataset, let's create some dummy dataset. For simplicity's sake, let's assume x as the length of the features of x as the features of length 10 and y to be the labels of again of length 10. Now we can use our myDataset class to create an object of dataset type. Let's look at the dataset index 0, which is asking for the information at the 0th index, and it is similar to calling the get item function at the given index. Sorry, I'll just run the above function, and yeah, here you see we have x values, y values, and this both dataset 0 and get item returns the same output. Moving on to the data loader. This is the class which actually handles the data loading logic. Data loader batches all the samples together, shuffles them in an efficient manner using parallel processing. Using the dataset class, so here let's first see an example and understand all the arguments we pass into our data loader. Using the dataset class we created above, we pass in the training data and the labels and creates an instance of that class. Along with that instance, we pass in some training arguments into our data loader function. These arguments are as follows. It includes shuffle. Here we pass in shuffle. Here we set shuffle equals to true when loading training data because you want to reduce the bias that your data might have from before. The batch size is of 256. So one batch will have 256 samples. Number of workers will be the number of workers you want to use for parallel processing. Number of workers 0 means it's in the main process. Pin memory is set to true if you have access to CUDA, and it typically makes it faster. So yeah, let's look at an example again. Here we see an example of how to use the data loader class. Notice we haven't passed any arguments here. So what would happen is that we have passed the object of the dataset class, which we have, and so the batch size would be 1 and shuffle will automatically be set to false. So when we access x and y, we get a PyTorch tensor of x and y of size 1. So yeah, and they are in a non-shuffled manner. Let's pass in some arguments now. Now if we pass a batch size of 2 and shuffle equals to 2, we can see that the data is now shuffled and we have 2 samples in a per batch. Now let's see one more example of custom image dataset. For this case, we create a dataset by initializing 2 empty lists and populating them with the training dataset we had before, which we loaded from the R Fashionist MNS dataset. Then we convert these lists to NP array. This is done because we are looking at creating our own data, and once we have that, we can save it to the .npy. As explained before, let's create a similar custom image dataset class. There is a constructor in it which accesses the images using np dot and does the np dot load on the image and the labels. Then we have the length of the dataset using the len function, and finally we can populate the get item which gives the information at the given index. In this case, since we are not processing anything, we are just returning it as it is. Here we look at another function called the collate function. So this is basically a data loader parameter which can be customized to achieve custom batching. That is, if you want to stack the data in dimension other than the first dimension, or we want to stack the data of different lengths, or we want to put together the data of different types. You may also apply some transformation in the collate function. One can choose to apply transformation in the collate function instead of the data class if the transformation needs to be applied on batches. Also, since DataLoader supports multiprocessing through multi-workers, hence collate function can take advantage of multi-worker performance speed up. Here you see we define the collate function inside the dataset class, but it's not at all compulsory. We can define it separately or as independently as we want it. So you see that we have a batch is given to us. We can first convert this to zip to get the x and y's, and now we can process it. Here we are doing a padding. For example, here we are padding the images in the given batch in order to make all of them of similar length and returning the x's and the y's. In future homeworks, we will do some other processing in the collate function, and it will come really helpful. So let's now create our dataset object using the custom dataset we have. We passed the file locations to the constructor. Now we have the custom object. We will see how we can pass other arguments to the data loader. So here we pass a batch size of 2 with shuffle equals to true and the collate function. As I mentioned before, here we passing the collate function as the method of the trained data class, but you can also define it separately and then pass it to the data loader. We see when in order to visualize it again, we can see that we use the iter function, the next function, and we can see our label of 0. So you can see a pattern in the here that similar will be used and the similar will be used in the future homeworks, wherein we will have a custom data set with len, the get item function that's used to create a data set object. This object is passed to a data loader and with arguments. Again, we use the iter function on the data loaders to create it to get the next batch. Then we do the indexing to take the first image in the first batch and then squeeze it, since we are not concerned about the channels, and we can see the output. Let's talk a little bit about the data transforms. Transforms can be applied to PIL images, tensors, ND arrays, or custom data during the creation of the dataset. This will be helpful in our homeworks for pre-processing the data and get better validation accuracy, basically avoiding overfitting and introducing less bias. We can compose multiple transforms and pass in a list of multiple transforms to be applied one after the other. So here we creating the train transforms and test transforms separately. And let's just extend our previous custom image data set to include the transforms as well. We pass in the we initialize the transform in our init function, and we call if the transform is available, we apply this transform in our get item on the image. As we can see that for test and train, we created different transforms for train and test, because for test or validation data we don't want to augment the data, as this is supposed to be used for testing only. Refer to the, as always, refer to the original documentation to check out the different transformations available, and you will learn more about what will be the right transforms for your data in the future homeworks. So like that's again in the finally in when creating a data set, this is how you pass in the transforms while calling the transform argument. Well, that's it for today. Thank you.